Introducing SkyEye, the first cooperative multi-principal IAM enumeration framework. Imagine you're pen testing an AWS environment. You've collected several sets of keys: access key, secret key, session token. Yet every scan you run tells a different, incomplete story. That's the core weakness of single principal IAM enumeration. Because each session can see only what its own identity is allowed to see, hidden permissions stay hidden, and critical attack paths slip right past your radar. To fix this blind spot, we introduced the cross-principal IAM enumeration model, CPIEM for short. Instead of testing each user in isolation, CPIEM coordinates all valid sessions simultaneously, letting every principal supplement the other's limited vision. The result? Hidden permissions surface. You see a truer end-to-end map of every policy and role. And those pesky false negatives, dramatically reduced. We'll now be delving deeper into how our algorithm works under the hood alongside a demonstration on how to use our features in the application. First, SkyEye validates every key pair you feed it, clusters them by account ID, then spins up a multi-threaded session per user. All those threads write to one shared NVM data vault per account, so when any session discovers a user, group, role, or policy, everyone else learns instantly. Single principal scans give each user a narrow cone of vision. CPM overlaps those cones, stitching them into a 360-degree IAM panorama, no blind spots. Let's go back to our introductory example to break down the whole steps. Here's a real-world crash test. 5 users, A through E, each hold a different sliver of IAM power. User A sees nothing. User B can read inline policies. User C lists attached policies. User D fetches policy versions. User E lists roles and groups. Run separately, they stay blind. Run together under CPIEM, their privileges interlock. User E's list roles exposes role A. User B's get role policy cracks it open. User D's get policy version reveals every statement, and so on, until every user, even user A, inherits the full picture. So we'll be demonstrating on how you would use the cross-principal IAM enumeration model in our application. Firstly, go to the ScanForm page on the sidebar. Within this page, there are 3 different forms represented by 3 different tabs up here. For this task, make sure you're on the multiple credential scan form. Set the scanning mode to cross entities. Allocate the number of threads that you want to use. Fill in the access key, secret key, AWS region, and optionally a session token. We won't be needing the session token for this demonstration. You can manually add more credentials or remove them, but for time's sake, we'll be using the Upload JSON credential feature. This feature will automatically populate your credentials list with your JSON file for convenience. Once populated, run the scan. This will take a couple of minutes depending on how many credentials you put in. The scanning will show you a live logging feed of what is happening under the hood as it is going through the IAM principles to craft your tree. Once the scanning is done, you would be taken to the session overview screen. This screen has a session banner on the top left which shows you the date and time of the session and the scanning mode of that session. We are currently using the multi-scanning cross-entity mode. Within the graphs, it'll give you the account clusters mentioned previously, along with all the users belonging to each account cluster. There will also be scan logs outputted, which you can view on the top right, but we'll be demonstrating that later. Let's go look at the IAM vision context of some of the users. They look nicely filled out. We'll be taking a deeper look at the AV1 user. As you can see within the graph, each user has an inline policy node, an attached managed policy node, a group list, and a role list. Each of the groups has their own inline policies and attached policies, same with the different roles. Now you may be wondering, why these roles have dashed lines connecting them together? That's because these are assumed roles that our algorithm uses. So what are assumed roles and how did we connect them like this? We'll be going through our transitive cross-role enumeration model to better understand how this works. Each user principal might have the permission to assume some specific roles and retrieve the temporary session tokens to act on behalf of those roles. Each role principal might also have the permission to assume the other roles and to act on behalf of those roles through temporary session tokens. That is the core idea of the transitive cross-role enumeration model, where it would collect as many in-scope roles as possible through the chain of assumed roles, whether directly from the given role or indirectly from the roles derived from the original role. Now, how would this help expand our IAM vision context? By assuming these roles in parallel, we're able to aggregate the different permissions and policy data from both the roles that we got from the user principal and the assumed roles we collected. That will further our IAM vision by extending our permissions and policy data from these assumed roles to create a more complete view of the user. This is applied in all of our enumeration models, so our single principal IAM enumeration model, separate principal IAM enumeration model, and most importantly, our cross-principal IAM enumeration model. Here's why TCREM matters once you plug it into CPIEM. As soon as user A assumes role A, role E, or any other hop, SkyEye pools those role-based permissions back into user A's profile, instantly widening the view. Now multiply that by every user in the account. User B, user C, user D, each with their own trust chains. TCREM spins up parallel sessions for every identity and every role they can reach, then shares the findings across all sessions through CPIEM's data vault. The result is a single cooperative scan that maps hidden privilege chains, indirect escalation paths, and misconfigured policies you'd never catch by enumerating one principal at a time. Now let's get back to our graph. We've discussed on how pivotal the roles are for forming our vision context, and how they are connected. Let's move on to our policies. When you click on a policy node, you will be taken to a policy view. Within the view, it will show all the parent nodes that leads up to that policy. And within each policy exist statements. Each statement will have a set of actions, and these actions belong to certain services. There are also different resources attached to these statements. Let's click on the Action node to see what we get. Within the Action view, there would be an Abuse Methodology node, a Relevant Commands node, and a TTPs node based on the MITRE attack matrix. When you click on the Redirect button on the TTP node, it will generate a new tab to show the MITRE attack matrix cloud table for you to get more detailed information on the tactics, technique, and sub-techniques for your action. You can also click the header to navigate straight to the MITRE attack website to get more details. Let's go back. For our table, you can filter and search with it, like so. If I wanted to see T1189, then it'll appear right here. You can collapse and expand it. There are two ways to get to this table. You can click on the Redirect button from our IAM Vision context graph, or you can click on the MITRE Attack Matrix Cloud button on the navigation bar. How did we compile this information for our action nodes? The TEP, relevant commands, abuse methodology, and action severity were all part of our own dataset in which we'll introduce now. SkyEye ships with a master dataset that classifies roughly 20,000 AWS API actions into 5 buckets: low, medium, high, critical, and a special Privy-esque vector tag short for privilege escalation. Low means read-only, non-destructive actions. Medium means actions that can modify non-sensitive configs. High means actions that can majorly change states or expose data. Critical means actions that can fully compromise the system, like wiping data or allowing root-level control. Privy-esque means actions that directly enables privilege escalation. For each action, it stores the risk bucket, a mapped MITRE attack tactic, technique, sub-technique, a short abuse methodology, describing how an attacker could weaponize it, and example CLI commands. This lets defenders instantly spot and remediate critical or priv-esque permissions and helps red teamers chain lower risk calls into high-impact attacks. By tying every permission to attack, SkyEye turns raw IAM results into immediately actionable threat intel for both blue team hardening and offensive simulations. Now back to our graph once again. Go back to the policy view and we'll check out the History Policy Versions node. This screen will show you the different policy versions in the default policy versions history, which is the policy version in the policy view. As you can see, this graph shows us 4 different policy versions, which is the max number of historic policy versions available to us, not including the default version. For each historic policy version, it works similarly to the regular policy node, which includes statements, a set of actions along with their services, and the resources attached to it. But there are slight differences, like a new action wrapper node that specifies whether or not it's an action or not action. The resource wrapper node also has a not resource instead of just resource. There are also new tags like kept or not changed, new, or even a removed tag, which gets grayed out for the rest of the graph. There are also no SID statements, which are statements that has no SID, but it will still have the same structure as the other historic policy versions. So, how does this actually work? How do we compare these historic policy versions so that we could tag them with the relevant tags? We'll be delving deeper on the mechanics of our deep comparison model for policy documents of active version and historical versions. Rolling an old IAM policy version back into production can be a gamble, because each customer-managed policy in AWS can keep up to 5 different versions, only one of which is active at any moment. SkyEye's deep comparison model removes that guesswork. First, it pulls every version of every attached customer-managed policy with a bulk IAM Getty Policy version sweep, capturing the live default and every archived copy. Then it lines the default JSON up against each older version, field by field, effect, action, not action, resource, not resource, and every nested condition, so nothing slips through the cracks. Each permission difference is color-coded and tagged. New, if the rollback would add extra power, kept, if nothing would change, and removed, if that permission would disappear. In seconds, a wall of raw JSON turns into a clear impact report. Blue team defenders can preview privilege drift before it happens and tighten least privilege, while red team testers instantly spot which dormant version would hand them a privilege escalation foothold. Tricky constructs like multiple resource blocks or sneaky not-action lists are all captured and clarified. SkyEye's deep comparison model lets you know exactly what will change before you flip the switch. Now that we've gone through quite a bit of the different models that SkyEye is built upon, let's take a look at the fundamental chain of actions that lets SkyEye enumerate IAM user principles, in-scope IAM groups, and in-scope IAM roles. First, SkyEye maps every identity that matters to our user, the groups they belong to, and every role they can assume, directly or by transitively hopping through other roles. With those in scope, entities in hand, the inline policy suite begins. Step 1, Users. We call IAM list user policies to list every custom policy name wired straight to the user. Then IAM get user policy to pull each JSON document. Step 2, Groups. For every in-scope group, we run IAM list group policies, followed by IAM get group policy. That surfaces permissions the user inherits just by being a member. Step 3, Roles. Any assumable role is treated the same way. IAM list role policies plus IAM get role policy to extract role-level inline grants. By chaining those 9 calls across users, groups, and roles, SkyEye captures every handwritten statement. No managed policies yet, only the bespoke rules that often hide risky one-off privileges. Next, we pivot to managed policies, the reusable blocks most organizations rely on. The flow is similar but a bit richer because versions come into play. User level. With IAM list. Attached user policies, we collect every policy ARN on the user. If allowed, IAM get policy or IAM list policy versions tells us which version is active, and IAM get policy version downloads that JSON. Group and role levels repeat the pattern with IAM list. Attached group policies and IAM list. Attached role policies. Version fuzzing fallback. When the account blocks the version listing APIs, SkyEye's multi-threaded version fuzzing algorithm brute requests IAM get policy version for versions 1 through 5 until it finds the default. Up to this point, we've taken a forward enumeration approach. Start with the user, then walk outward, groups, roles, and finally every policy that hangs off those identities. That works well, but it can miss things whenever the account blocks an early API call or when the same policy is reused in unexpected places. To plug the gaps, SkyEye flips the telescope around and runs an inverse enumeration. The engine grabs each managed policy ARN it has discovered, customer or AWS managed, and calls IAM list entities for policy. That single API returns every user, group, and role that consumes the policy. Now, instead of asking what policies belong to this user, we're asking what users belong to this policy. If the session has power to invoke IAM list policies with scope equals all and only attached equals true, SkyEye pulls the master list first, prioritizing the policies it already knows are attached. When those scopes are blocked, it falls back to a curated set. All public AWS managed policies plus the customer policies it gathered earlier. Either way, each ARN flows into list entities for policy until every hidden attachment path is exposed. SkyEye has a nuclear option for IAM reconnaissance. IAM get account authorization details. Instead of chaining dozens of calls to list users, groups, roles, and every inline or managed policy, this single API dumps the entire authorization picture for the account in one shot. When SkyEye detects that any session, user, or assumable role can invoke it, SkyEye halts every other thread, fires this call once, and pulls back the full JSON. From there, the framework programmatically filters the result down to just the targeting user, their in-scope groups, and their in-scope roles, so you're not drowning in irrelevant entities. The payoff is huge, about 95% shorter scan time. Hidden permission overlaps, conflicts, or escalation paths that could slip past piecemeal enumeration pop out immediately, all with one API and one pass. So now we'll be scanning the same credential set using the separate principal IAM enumeration model instead of the cross model. This model supports scanning by principal-specific IAMs utilizing relevant IAMs permissions, which is like the cross model, but without the aggregation of the permissions from different users, hence the name separate. So it is quite limited, however. We've still implemented it into our framework for certain use cases. So from the home page, navigate to the scan form page. Make sure you are on the multiple credential tab. Set the scanning mode to separate entities, allocate the number of threads, and add your credentials. Once the scanning is complete, we're taken to a familiar graph as we've used the same credential set with only a slight change in the mode title. Now going through each user, you can see how limited it is compared to the cross-enumeration model. A lot of no access from every user, so let's move on to demonstrating the single principal IAM enumeration model. The single principal IAM enumeration model is essentially the same as the separate principal IAM enumeration model, but it's for a single entity and you can't scan with multiple credentials. So it's exactly the same and it will yield the same results, so we will not be using the same credential set for it. Because for our framework, we've added fuzzing capabilities and permissions simulation capabilities to the single principal IAM enumeration model, and we wanted to showcase that feature instead. Now, navigate to the Scan Forms page. Make sure you're on the Single Credential Scan tab. The mode for single user will always be separate entities, no matter what. Allocate the amount of threads that you want to use and enable the IAM fuzzing option. So what is IAM fuzzing? So the IAM fuzzing algorithm that we implemented in our framework starts with an IAM user and any roles they might later assume. If the session is allowed to call IAM simulate principal policy, we feed that API nearly 20,000 actions scoped to every resource. The service evaluates all policies on the user and on any groups the user belongs to and returns the actions explicitly allowed. Because simulate principal policy can't see privileges the user would gain by switching roles, we pair it with our transitive cross-role enumeration model, which discovers every role the user can hop into, directly or through chains, and we rerun the same simulation for each of those roles. This was previously covered. The combined output becomes our authoritative allowed actions list. If the user can't run simulate principal policy, we drop straight into a fallback, read-only fuzzing. In that mode, we actively invoke roughly 8,000 AWS read-only actions. Calls that succeed reveal permission, and calls that fail log as denies, because these read-only methods rarely need extra parameters. Finally, whichever path we used, or both, we merge the results into an output JSON file to display into a graph on the front end. Now that we have grasped a better understanding of how SkyEye handles the IM fuzzing process, we'll be showcasing both scenarios for the fuzzing algorithm. One scenario is for the credential that has the permission to invoke the simulate principal policy, and the other scenario with a credential that does not have the permission. So, we've already plugged in the credential that has the simulate principal policy permission, and we'll begin scanning. Once the scanning is done, you'll see that the session overview screen looks a bit different. You won't be able to click on the user node, but instead it has two graphs for us. One is the separate single scan graph, and the other is the fuzzing graph. We're mainly interested in the fuzzing graph though, so clicking on that shows us quite a populated graph. Navigating deeper shows that the simulate algorithm definitely worked wonders and revealed a lot of the IM vision context for this user. Compared to the fuzzing graph, the separate graph shows a lot of no access, showing its limitations in exploring the IM vision context. Let's move on to the second scenario where the user does not have permissions to invoke simulate principal policy. So we've already filled in the credentials that lack the permission to invoke simulate principal policy, so it'll carry out the fuzzing with 8,000 AWS actions instead. Start the scan. Once the scanning is done, we're greeted with a similar graph to the last scenario in the session overview screen. This time, the separate graph has no access at all. And the fuzzing graph is very different to the first scenario. It will only have the user with a set of actions connected to their services. It's not as detailed as the simulate principal policy fuzzing process, but it gives you a good idea on what kind of actions this user can exploit within the system. You can also filter out the services to make the analysis process a lot easier. One of the features that our web app offers is the scan logs. Just navigate from the home page to the scan logs on the sidebar. In this screen, you can see all your past scanning sessions logs. You can filter them based on the session status. You can search specific logs using the scan ID or the date time. You can also view in detail by click on the eye on the actions column. Within the log detail screen, you can see the logs recorded from that session, the date time of the session, status, duration, and the type of that session. You can also download the logs by click on the download button on the action column. We've also incorporated into our web app the dataset that we talked about before, where the AWS actions are linked and mapped to the different abuse methodologies, MITRE ATT&CK TTP, and relevant commands. From the home page, navigate to the action dictionary in the sidebar. As you can see, the table displays the services, action name, TTP, abuse methodology, and relevant commands. Some of the actions do not have commands, but if you were to go to a different page, then you'll find some actions with relevant commands for you to start exploiting. You can search by action name or methodologies. If I wanted to search using the create investigation action name, then I can do so. If I wanted to search using the methodology like adversary ads, then I can also do that. You can also filter by services on the top right side. Let's say you only wanted to see actions within the Connect service. Then there you go. There would only be Connect actions. If you want to get further information, then you can visit our GitHub, Gitbook, and/or paper that we've listed here. Thank you very much for watching our demonstration.